Welcome! In this session, we'll be tackling an interesting and challenging problem, problem number 2007, find original array from doubled array. We'll explore the problem statement, break it down step by step, and review different approaches to solving it. Let's dive in. The problem begins with an array called changed. This array is created by taking a non-empty array, which we'll call original, and appending twice the value of each of its elements to the array. Once this new array is formed, it's shuffled randomly to create changed. Your goal is to reverse this process to find the original array from the given changed array. However, there's a catch: if it's not possible to reconstruct the original array, you should return an empty array. The input is given as a single integer array changed, and the output will either be the reconstructed original array or an empty array if reconstruction isn't feasible. Now let's look at some examples to understand this further. For the input changed equals 1, 3, 4, 2, 6, 8, the output is 1, 3, 4. Here's why: if the original array is 1, 3, 4, doubling each element gives us 2, 6, 8. When these two arrays are combined and shuffled, we get 1, 3, 4, 2, 6, 8, which matches the changed array. However, in the next example, where changed equals 6, 3, 0, 1, it's not possible to split the array into an original array and its doubled version. So, the output is an empty array. In the third example, the input is changed equals 1. Since there's only one element, it's impossible to form a valid doubled array. For this reason, the output is also an empty array. This highlights an important aspect of the problem: if the changed array has too few elements, or if its structure doesn't allow for pairing elements with their doubles, we should return an empty array. This is why careful analysis of the array is necessary to determine whether a solution is possible. Finally, let's consider some edge cases. If the changed array has fewer than two elements, such as 1, or an empty array, it's immediately impossible to form a doubled array. For arrays that consist entirely of zeros, like 0, 0, 0, 0, we need to ensure there are enough zeros to pair them properly. Lastly, in cases where there are mixed values, such as 1, 3, 6, 12, the challenge lies in determining whether all elements can be matched with their doubles without any leftover values. These scenarios test the robustness of the solution, so it's essential to handle them correctly. To start, let's think about the most straightforward way to approach this problem: a brute force solution. The idea here is to generate all possible subsets of the array and check if any of these subsets, when doubled and shuffled, can reproduce the original input array changed. This involves iterating through every subset, finding a valid doubling relationship, and checking if the constraints of the problem are satisfied. However, while this approach is intuitive, it's computationally impractical. Generating all subsets has a time complexity of O2 to the power of n, which grows exponentially. Given that changed can contain up to 100,000 elements, this approach is infeasible for large inputs. So, while it helps us understand the problem, we need a more efficient strategy to solve it in practice. A much more structured and efficient strategy is the frequency mapping approach. Here, we use the key insight that if changed was derived from doubling an original array, the smallest element in original must correspond to the smallest element in changed. This leads us to a systematic way of processing the array. For each element x in original, there must be a corresponding 2*x in changed. By sorting the array, we ensure that smaller numbers are processed first, which avoids issues like mistakenly pairing a doubled value with an overlapping number. The steps are straightforward. First, we count the frequency of each number in changed using a hash map. Then, we iterate through the sorted array, processing each number in order. If a number x is already used, we skip it. Otherwise, we check if 2*x exists in the map. If it does, we decrement the frequencies of both x and 2*x. If not, the array is invalid. Successfully processed numbers are appended to our result, which ultimately reconstructs the original array. The time complexity of this approach is a significant improvement. Sorting the array takes n log n, and iterating through the array while updating the frequency map takes n. This makes the overall complexity n log n, which is manageable for large inputs. The frequency mapping approach was chosen because it is both efficient and intuitive. The key realization here is that sorting ensures correct pairing of elements, while the frequency map efficiently tracks the availability of numbers. This method avoids the pitfalls of brute force and delivers a solution that balances simplicity with performance. When comparing the brute force approach to the optimized frequency mapping strategy, the trade-offs become clear. The brute force method, with its O(2 to the power of n) complexity, is completely infeasible for large arrays, whereas the optimized approach brings this down to O(n log n) by eliminating unnecessary subset generation and directly focusing on pairing elements. While sorting introduces an additional O(n log n) cost, it simplifies the pairing logic and ensures correctness, avoiding the need for more complex data structures. In terms of space complexity, the frequency map uses O(n) space, which is a reasonable trade-off given the efficiency gains. Overall, the frequency mapping approach stands out because it combines clarity, efficiency, and correctness. By leveraging the observations about pairing and sorting, it avoids redundant computations and provides a clean solution to the problem. The problem we're tackling involves reconstructing an original array from a given changed array, such that every element in changed is exactly twice an element in original. If this pairing is possible, we return the original array, otherwise, we return an empty array. To solve this, the first step is to validate the input. Since pairing elements requires an even number of values, the first check is to see if changed has an odd length. If it does, we can immediately return an empty array. Next, we sort the array in ascending order. Sorting is a crucial step because it allows us to process smaller elements first, ensuring that pairs are matched correctly. For example, smaller elements like 2 must be paired with 4 before we consider larger elements such as 8 or 16. This step lays the foundation for the algorithm's logic. Now, we move on to building the frequency map. This map will store the count of each element in the changed array, and it's vital for efficiently tracking and matching elements with their doubles. For instance, if changed is 4, 2, 2, 8, the frequency map would be 2, 2, 4, 1, 8, 1. With this structure in place, we can now iterate through the sorted changed array. During this iteration, we initialize an empty list called original to store the elements of the reconstructed array. For each element x in changed, we first check if its frequency is 0. If it is, we skip it because that means x has already been paired. Next, we check if 2*x exists in the frequency map with a non-zero count. If it does, we append x to original and decrement the counts of both x and 2*x in the frequency map. However, if 2*x is not available, pairing is impossible, and we return an empty array. This process continues until all elements are processed. Several key insights make this solution efficient and robust. First, sorting the array is essential because it ensures that smaller numbers are processed first, which is critical for correctly identifying pairs. For example, processing 2 before 4 ensures that we pair them appropriately before moving on to larger numbers like 8. Second, the frequency map is the backbone of this algorithm. It allows constant time access to check and update counts, making the pairing process efficient. Third, handling edge cases properly is crucial. The algorithm relies on the presence of exact doubles, so if an element like x cannot find 2*x in the frequency map, pairing fails, and the algorithm terminates early. Finally, the two main data structures here are the frequency map, which tracks counts efficiently, and the original list, which stores the reconstructed array that we return if pairing succeeds. When we analyze the complexity of this algorithm, the sorting step dominates the time complexity, taking O(n log n), where n is the length of the array. Iterating through the array, along with frequency map operations like insertions and updates, runs in O(n). Combining these, the overall time complexity is O(n log n). In terms of space complexity, the frequency map requires O(n) space to store counts, and the original array also takes O(n) space to store the result. So, the total space complexity is O(n). It's also important to address key edge cases. If the changed array has an odd length, we immediately return an empty array since pairing is impossible. Zeros require special attention because they must be paired with other zeros, so we need to ensure there's an even number of them. Lastly, when working with large numbers, the algorithm must handle cases where no valid doubles exist, such as 1, 3, 6, 12, or 3 cannot find a matching double. These considerations ensure the algorithm is both efficient and robust across a variety of inputs. To solve the problem of finding the original array from a doubled array, we begin by checking an essential condition. If the length of the input array, changed, is odd, it's impossible for it to represent a doubled array, so we immediately return an empty list. Next, we use the counter class from the collections module to count the occurrences of each number in the array. This helps us understand the frequency of each element, which is critical for reconstructing the original array. We then handle a special case for zeros. If there are zeros in the array, their count must be even since each zero needs to pair with another zero to form a valid doubled pair. If this condition isn't met, we return an empty list. After this, we sort the keys of the frequency dictionary in ascending order. Sorting ensures that we handle smaller numbers first, which is necessary because doubling smaller numbers can affect the counts of larger numbers. Finally, we initialize an empty list, original, to store the reconstructed original array. At this point, we begin iterating over each number in the sorted list of keys. If the current number has already been fully used up during processing, we simply skip it. Additionally, for zeros, we calculate how many of them can contribute to the original array by taking half of their count and extending the original list accordingly. Once zeros are handled, we continue processing the other numbers in the sorted list of keys. For each number, we check if there are enough occurrences of its double, 2*x, to pair with the occurrences of x. If there aren't, the array cannot be valid, so we return an empty list. On the other hand, if there are enough doubles, we add x to the original array the number of times it appears in the input, which is given by count, x. Then, we reduce the count of 2*x by the same amount, as those elements have now been used to form pairs with x. This ensures we correctly track the remaining unused elements in the array. After processing all numbers, the original list contains the reconstructed array that, when doubled, matches the input array. Finally, we return this original list as the result. Here, we begin by importing the necessary libraries and defining the solution class with the findOriginalArray method. The first thing we check is whether the length of the input array changed is odd. If it is, it's impossible for the array to be a valid doubled array, so we return an empty array immediately. Next, we use a tree map to count the occurrences of each number in the array. A tree map is chosen specifically because it keeps the keys sorted, which is important for processing the elements in ascending order later. We then initialize the original array with half the size of changed, because the original array will only contain the undoubled elements. We also set an index variable to keep track of our position in the original array. After initializing these variables, we start iterating through the keys of the tree map to process each unique number in sorted order. For the special case of zeros, we ensure that their frequency is even, as zeros can only pair with other zeros. If the frequency is odd, we return an empty array since it's invalid. If the frequency of zeros is valid, we add half of them to the original array by iterating frequency/2 times and assigning zeros to the array. After handling zeros, we move on to other numbers. For a number x, we check if there are enough 2*x values in the map to pair with all occurrences of x. If there aren't, the array is invalid, so we return an empty array. If the condition is satisfied, we add x to the original array frequency times, where frequent is the count of x. After adding x, we reduce the count of 2*x in the map by frequency, because those values have now been used to pair with x. This process continues for all numbers in the map. Finally, once all numbers are processed, we return the original array, which represents the undoubled version of the input array. This ensures that the logic is complete and the array is reconstructed correctly if valid. To solve the problem, we start by examining the input array changed, which is 1, 3, 4, 2, 6, 8. The first step is to check if the length of the array is even because a valid doubled array must have an even number of elements. Since the length is 6, which is even, we proceed. Next, we count the frequencies of each number in the array using the counter function. This gives us a frequency map: 1, 1, 3, 1, 4, 1, 2, 1, 6, 1, 8, 1. Each number appears exactly once. After that, we sort the unique keys in ascending order to process them systematically. The sorted keys are 1, 2, 3, 4, 6, 8. Now, we process each key in the sorted order to construct the original array. Starting with the smallest key, 1, its frequency is 1, and the frequency of its double, 2, is also 1, which forms a valid pairing. We add 1 to the original array, making it 1, and reduce the counts of both 1 and 2 to 0. Next, we move to the key 2, but since its count is now 0, we skip it. For the key 3, its frequency is 1, and the frequency of its double, 6, is also 1, another valid pairing. We add 3 to original, updating it to 1, 3, and reduce the counts of 3 and 6 to 0. For the key 4, its frequency is 1, and the frequency of its double, 8, is also 1, forming yet another valid pairing. We add 4 to original, making it 1, 3, 4, and reduce the counts of 4 and 8 to 0. Finally, the keys 6 and 8 are skipped since their counts are 0. At this point, the count map shows all values as 0, indicating successful processing. The final output for this example is the original array, which is 1, 3, 4. We return 1, 3, 4 as the result. Now, let's analyze another example where the input is 6, 3, 0, 1. Once again, we begin with an initial check. The length of the input array is 4, which is even, so we proceed. Using counter, we calculate the frequencies, resulting in 6, 1, 3, 1, 0, 1, 1, 1. Sorting the unique keys gives us 0, 1, 3, 6. As we process the smallest key, 0, we find that its frequency is 1, which is odd. This immediately invalidates the input because a doubled array cannot have an odd count for any number. Therefore, we return an empty array right away. In this third example, the input array is 1, 2, 2, 4. We start with the initial checks, and the length of the array is 4, an even number, so we proceed. Using counter, we calculate the frequencies, which gives us 1, 1, 2, 2, 4, 1. Sorting the unique keys results in 1, 2, 4. These steps set the stage for processing each key. We begin processing the keys in sorted order. For the key 1, its frequency is 1, and the frequency of its double, 2, is 2, forming a valid pairing. We add 1 to the original array, making it 1, and reduce the counts of 1 and 2 accordingly. Next, for the key 2, its updated frequency is now 1, and the frequency of its double, 4, is 1, another valid pairing. We add 2 to original, updating it to 1, 2, and reduce the counts of 2 and 4 to 0. For the key 4, its count is now 0, so we skip it. At this point, all keys are processed, and the frequencies in the count map are 0, indicating success. The final output is 1, 2, which we return as the result. To analyze the time complexity of our solution, let's break it into its component steps. First, we use the counter function from the collections module to count the frequency of each element in the input array changed. This step runs in n time, where n is the length of the array, since we iterate through the array once. Next, we sort the keys of the counter dictionary using Python's sorted function. Sorting these keys has a time complexity of k log k, where k is the number of unique elements or keys in the array. In the worst case, where all elements in the array are unique, k equals n, making this step n log n. Finally, we iterate through the sorted keys to verify if each key can form a valid pair with its double, 2*x. This loop processes each unique key, so it runs in k time. For each key, the operations checking counts, updating the original list, and adjusting counts are 1 per operation. Thus, this step takes k overall. These steps together give us an intermediate understanding of how the algorithm scales with the input size. The time complexity analysis continues with the step of constructing the original array. In this step, we extend the original list by appending elements based on their count in the counter. Each element is added exactly once to the original array, so this step runs in n time. When we combine all the steps, the overall time complexity is determined by the most time-consuming operation, which is sorting the keys. This makes the final time complexity n log n. Now, looking at space complexity, the primary contributors are the counter dictionary, which stores the frequency of unique elements, the sorted list of keys, and the original array. The counter dictionary requires O, K, space, which simplifies to O, N, in the worst case when all elements are unique. Similarly, the sorted keys require O, K, space, which is also O, N, in the worst case. These are the first components of the space complexity breakdown. Another major component of space complexity is the original array itself. Since the input array changed has a length of 2m, the reconstructed original array will have a maximum length of m, which is n/2. This means the space required for the original array is O, n. Summing all the components, the total space complexity amounts to O, n, for the counter, O, n, for the sorted keys, and O, n, for the original array, giving us a final space complexity of O, n. To compare with a naive approach, consider an algorithm that repeatedly searches for pairs x and 2*x in the array. This would involve nested iterations and result in a time complexity of O, n squared. By contrast, the optimized solution reduces the time complexity to O, n log n, by leveraging a hash map for counting and sorting the keys. Importantly, the optimized solution maintains consistent time and space complexities of O, n log n, and O, n, across best, average, and worst cases, as the algorithm always involves sorting and iterating through the keys. To solidify the time complexity analysis, we can look at the mathematical proof of the big O notation. The sorting operation, with its O, n log n, complexity, dominates the overall time complexity because it grows faster than any other step as the input size increases. All other operations, including counting, iterating through keys, and constructing the original array, are either linear, O, n, or constant, O, 1. These operations have a negligible impact on the asymptotic complexity compared to the sorting step. Thus, the final time complexity is O, n log n. For space complexity, the primary contributors, the counter dictionary, sorted keys, and original array, all scale linearly with the input size, leading to a total space complexity of O, n. These analyses confirm the efficiency of our solution in both time and space usage. One of the most common mistakes in this problem is not handling duplicate elements correctly. For example, if the input array is 2, 2, 4, 4, some solutions might mistakenly pair the first 2 with the first 4 without considering all possible combinations. To avoid this, it's important to sort the input array and explicitly track the frequency of each number. Another frequent issue is assuming the array always has an even length. If the array length is odd, it's impossible to split it into valid pairs, so checking the input length should be your first step. A third mistake involves directly modifying the input array while iterating through it. This can cause elements to be skipped or processed incorrectly. Instead, use a separate data structure, like a dictionary or a counter, to manage frequencies. Lastly, be cautious with brute force solutions. Generating all subsets or trying all pair combinations can result in an exponential time complexity, which becomes impractical for large inputs. Optimizing with sorting and hash maps is key to handling this efficiently. Now, if the problem allows negative numbers, your solution must account for them. For instance, the pairing logic should handle both positive and negative values if they're part of the input. Alternatively, you should clarify with the interviewer whether negatives are excluded. Speaking of interviews, this problem is a great example of pairing elements based on specific conditions, such as doubling or halving. Sorting the array and using a frequency map are standard strategies for these types of problems. During an interview, it's crucial to communicate your thought process clearly. Start with a straightforward brute force approach to show your understanding, then explain how you would optimize it with sorting or hash maps. Be ready to discuss edge cases, such as empty arrays, arrays with all zeros, or inputs where no solution exists, as this demonstrates attention to detail. Finally, be prepared to analyze the trade-offs of your approach, including time and space complexity, and discuss alternatives like in-place modifications versus using extra space. This problem shares similarities with other well-known LeetCode problems. For instance, LeetCode 1, 2sum, uses hash maps to efficiently find pairs, while LeetCode 15, 3sum, and LeetCode 18, 4sum, extend the logic to larger combinations by leveraging sorting in pointers. A closely related problem is LeetCode 954, array of doubled pairs, which is essentially a variation of this challenge. When considering alternative approaches, sorting combined with a frequency map is one of the most practical solutions. You sort the array, then iterate through it while using a hash map to track frequencies. Although this approach has a time complexity of O n log n due to sorting, it's typically efficient and straightforward to implement. Another option is the two-pointer technique, where you use 2 pointers on a sorted array to find valid pairs. While this can be faster in some scenarios, it requires careful handling to ensure elements aren't reused incorrectly, which can make the implementation more complex. If you explore brute force as an approach, it involves generating all subsets or trying all pair combinations. This method is simple to implement but has a prohibitive time complexity of O(2 to the power of n, or worse, making it unsuitable for larger inputs. Another alternative is modifying the input array in place to track used elements. While this saves space, it often leads to bugs, such as skipped elements, and can be much harder to debug or adapt. Each approach has its trade-offs, so it's important to weigh simplicity, efficiency, and the constraints of the problem when deciding on a solution. Ultimately, understanding the strengths and weaknesses of these methods will help you tackle similar problems effectively and confidently discuss your choices in an interview setting. Great work! To wrap up, we've summarized the solution and highlighted the key takeaways for this problem. Remember, mastering concepts like frequency maps and edge case handling is essential for tackling similar challenges. Thanks for your time, see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!